Okay, as promised last time, today we are going to do a design problem. And we reviewed these design steps, we looked at these design steps last time. Basically what you have to do is we start with a finite state machine and we have to set up our design table and then to enumerate the transitions and the output, and then we have to use our excitation table to figure out the desired inputs to the state registers. And then after we figure that, after we list those from the excitation tables, then we construct our kernel maps to get minimized two-level and/or circuits. And of course, if we were doing this in the real world, we would have to have two-level or and circuits as well. And for those of you who like to use exclusive OR gates, we would have to explore all these other different possibilities for implementing. Anyway, I just thought I'd throw that in. Okay, so let's go ahead and proceed. Now, here's the way I would like for us to proceed today. Let's not have anybody peek ahead at the next slide on your laptops or anything. And let's see if we can go around the room and work through this design problem. We'll just do this one design problem and we'll do all the bloody details, all the ones and zeros, all the kernel maps, and we'll wind up with a circuit, which is unknown, which is what we're trying to figure out. So we will start with figure 11.32, which is the finite state machine that we want to implement with our circuit. And like we said last time, because there are 4 states, there are how many flip-flops?
2.
2. And it has to be given what kind of flip-flops to use to implement it. And in this problem, we are going to use SR flip-flops. Are you with me? So that's given. And so we know that there's 2 of them. And so the first thing we have to do is construct the table. Now, actually, you guys, constructing the table is part of the problem. You know, knowing what to put in your table is kind of like part of the problem whenever you do these exercises. It's kind of like when we were doing the analysis, you know, we had to figure out what to put down on our table. So so tell me, from this finite state machine in figure 11.32, what does it tell us? It tells us what? What does each transition tell us? It tells us that if we're in a given state and we have a given input, what the next state is. So I think what we have to do is we just need to tabulate that. Are you with me? So the way to tabulate that is let's have initial state and initial input. So here's what our table will look like. Our table will look like, and let's call the first flip-flop A and the second flip-flop B. Are you with me? So we will have A at time t, B at time t. So this is going to be a long table. All right, a wide table. So here we have A at time t, B at time t, and then for each one of these we have a what? An input at time t. So let's call our inputs, I think we call them x1 and x2. Yes, so we'll call our inputs, so that's x1 at time t and x2 at time t. So we'll go like this. And so now what we have to do is do all the possible combinations here. But now here comes, what was our little tip that we used whenever we were implementing one flip-flop from another one. We said that because we can look ahead and we know that we're going to be transferring these things. Yeah, we know that we're going to be transferring them to Carnot maps. And so I think, just looking ahead, I think it's going to help us if we do if you list when you're doing a design problem, if you will list these things thinking ahead about how you're going to transfer them to a Carnot map, because otherwise the Carnot maps it's in different orders, and then you have to flip things around. You know what I mean? And if you flip them around in your head, then you can it's easy to make a mistake. So here's what we're going to do. Let's have these be in the Carnot map let's have the A and the B be in the Carnot map order. You see what I mean? Mm-hmm. And so in the Carnot map order, it's going to be what? 0, 0, 0, 1, but then what? 1, 1, 0. Now,
is this the design table?
This is the design, yeah, this whole thing is going to be the design table. And we're going to have and in the end, over here, what we're going to have is the desired inputs that we need for SR inputs. Now, does everybody see, because we have 4 states, right? But now looking at the figure 11.32, what are the possible input combinations that we have for X1 and X2? Can we, we have 0, 0, no, do we have 0, 0?
Oh, that was the don't care condition, right?
Yeah, look at figure, if we look at state 0, 0, how many possible transitions do we have out? How many transitions do we have out of each state?
3.
3, and they are always on which combinations of input?
1, 0, 0, 1, and 1, 1. So 0, 0 is a don't care.
Yeah, 0. So can you tell from here that 0, 0 is a don't care input? We don't expect that to happen. So that can be a don't care. Now, it might be that, like if we had 3 states instead of 4, it might, and you should be able to do this, by the way. If I give you a problem with like 3 states instead of 4, you should be able to use, one of those states as a don't care. And think about how you would construct the table that way. Are you with me on this?
So the states are the ABs, right? And the transitions are the X's?
Yeah, that's going to be our notational convention, is to have the X's be the inputs and the letters be the states. And it's flip-flop A and flip-flop B, Okay, so we don't have 0, 0. So all the possible ones here are what? 0, 0. So this would be for 0, 1. 0, 1, 0, 1, 0, 1. Are you with? Do you see what we're doing here? So it's from each one of these states, and then X1, X2 will be 0, 1, 0. And so how many rows are we going to have on our table, actually?
12.
Just 12. This time we'll look ahead. All right. And we might as well do, these are going to be part of the Carnot map. So the next ones we should do here is what? We should do 0, 0, 0, 1, 1, 1, 1, 0. But here we should do what? This is 0. So 0, 0 would be there. 0, 1. So this should be what?
1, 1.
This should be 1, 1. So 1, 1, 1, 1, 1, 1, 1, 1. And then this, again, would be what? 0, 0, 0. Yeah, hold on. Let me finish here. So this would be 0, 0, 0, 1, 1, 1, 1, 0. And now this will be what? All these will be what? 1, 0, right?
Yeah, 1, 0.
Okay, now, question?
How can you tell from looking at it that 0, 0 is don't care?
The way you can tell that 0, 0 is don't care is because there are no inputs with 0, 0. Are you with me? So because they don't exist, because they don't appear here, we say, we don't care what it does if there's a 0, 0 input. Are you with me? By the same token, if we wanted to implement a finite state machine with 3 states, it would be the state that doesn't appear that would be a don't care. So it's whatever doesn't appear in the finite state in the state transition diagram is the one that you don't care.
So say a state was a don't care, would we still want to write all, like say 0, 1 was the don't
Yes,
care
yeah.
We'd still want to write it.
You would still want to write it here, but every other entry would be don't care.
So how come we don't write the 0, 0 for the input? We're just going to skip that part in there?
No, what we'll do is when we do the Carnot map,
Just skip
we will know that an input of 0, that all four will be X's.
Okay.
Yeah, in
But with the
a
states,
Carnot
it's
map.
better to actually write down
Yeah,
the X's.
yeah. Yeah, that's what I recommend. These are all really good questions. Is everybody, are we good? Okay, now, so now what we need is we need one column, we need another column here for our output. So this is y at time t. Okay? So that's the current output. And now, can you tell, now, let's go ahead and label our, that was kind of crooked. Let's make that a little more straight. Okay, and now can you tell me what's going to be on the rest of the table? What's going to be?
What y of t is.
Well, we'll fill that out. Say it again. Yes. Now what we need to do is we need to enumerate from the finite state machine what a at time t plus 1 and b at time t plus 1 is. And then we will have to figure out, using the excitation table, what the S and R needs to be in order to make that transition. Are you with me? So that was a good call. So that was A. So what we want here is A at time t plus 1 and B at time t plus 1. Is everybody clear on this? All right. And now, actually, let me make this a little smaller. Okay. And then we will do that. And now tell me now how many circuits do we need?
Oh.
Well, sorry, not circuits. How many, so
do we need like SA?
how many output, you know how we have, in general, we have this, I don't want to scroll back, but you know, in general, we have the state registers, and then we have the feedback, and it goes into this big combinational circuit, and then the output of the combinational circuit. How many outputs of the combinational circuit do we have feeding into the registers?
4.
4. We have S, we have the SR for the A flip-flop and the SR for the B flip-flop. So now we've got 4 more columns. Now, is everybody with me on that?
Yeah.
Okay. So those are going to be, so let's call this one, let's do FF, we'll put flip-flop A here, and we'll put flip-flop B here. And what we have here is, this is going to be S at time flip-flop A. So well, let's call that SA. Are you with me? So that's the A input of the sorry, that's the that's the S input of the A flip-flop. So let's have SA at time t, RA at time t, and then for flip-flop B, we'll have SB at time t and RB at time t. And that's going to be desired. So we got 1, 2, yeah. Phew. Now, is everybody clear on the process? So now what let's do is let's go around the room. We started at the front last time. We'll start at the back this time. Okay. And first thing that we'll do is we have to go from the state transition diagram to the table. So let's do the column for y at time t. And now, how in the heck are you going to figure this out? So we are in, what are we saying? We are in state 0, 0. And if our input is 0, 1, so the back row now, input 0, 1, 0, 0, and if the input is 0, 1, then the output is 0. Okay, so now, does everybody see where he told us that?
Can we do the A of t plus 1?
No, let's go, yeah, I'd rather go down, sorry. Okay, so, but does everybody see that? Are you with me? Okay, so now we're going to go this way on our way up. Okay, so what's y at time t for this one? Oscar, Do you know? 0. Now, I'm not going to check this. So is everybody checking? And so if there's any challenges, speak up. Is everybody checking? Okay, next. Okay, any challenges? Next.
0.
0. Next. Sam. Oh, it should, because I thought we did all. So we're at state 0, 0, and the input is 1, 1. Then,
Okay, so it's 0.
okay, 0. Okay, next. 0. Next.
1.
Hold on. Oh, 1, you say?
Sorry.
Next.
1.
You thought you were going to do that one. Okay, next.
1.
1. Next.
1.
1. Next at the bottom. Now we're starting over at the back. 0. And next. 0. Now, does everybody, do we have consensus? Are we good? Now, here's the thing. Now, let's do these a pair at a time, right? Because if we're in state 0, 0 and we have a 0, 1, what state will we go to? Are you with me? So, and the state, because they're, right next to each other up there. Okay, so next, what is, if we're in state 0, 0 and we have an input of 0, 1, what's the next state? Okay, if we're in state 0, 0 and we have an input of 0, 1, what is our next state? 0, 0. Okay, next. If we're in state 0, 1 and we have a 0, 1, what's our next state?
Wait, I
Oh,
don't think that's right.
oh, challenge?
Yeah.
On 0, 1,
Okay.
we should go to 0, 1.
Do you want to read, do you? But do you see where you went wrong there? I mean, are you with, okay, make sure we got this.
0, 0 is the next.
This one you're saying is 0, 0?
Yeah.
Do you have this one?
Yes.
Okay, good. Okay, so, okay. Sam. You guys out there should be thinking about this too.
1, 0.
1, 0. And next?
1, 1.
1, 1. Okay, next?
1, 0.
1, 0. You sound kind of tentative there. 1, 1.
1, 1.
1, 1.
0, 0.
0, 0. Okay, last row. 1, 0. Now, you guys checking? You're getting whiplash. Like watching a ping pong match or tennis match. Boom, 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 boom. You're not joking. You really have whiplash. If we're in state 0, 1 and our input is 1, 0, what's our next state? Sounds like no one's challenging. Next. 1, 1?
0, 0.
Oh, oh, you're trying to say, okay, so, but you're saying it's 0, 0.
Yes.
Okay, and next? 1, 0. Now, is everybody, do we have consensus? Mm-hmm. Now, do you guys remember the excitation table for SR? Oh, question? Okay, which one are you asking the question about? The last one or the penultimate? This one? This one here?
You had the third to last one.
You had this one. Okay, so if the current state is 0, 1, so that's here. Are you with me? And the input is 1, 0. So if we're here and our input is 1, 0, this is the input 1, 0 coming from this state. Are you with me on that? And it goes to state 1, 1. That's why. Huh? No, 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 no. This is a single-sided arrow. This arrow from 0, 1 to 1, 1 is a transition from state 0, 1 to state 1, 1 on an input of 1, 0. And furthermore, the current output is 1. So you see how that got the 1, 1. Good. Is everyone clear on this? I know this can be confusing, and once you get a little bit off, and then pretty soon there's ones and zeros floating all over the place, you don't know what the heck's going on. But anyway. Okay, but now you guys, what about this? How in the heck do we do this? So, and which columns do we look at, and how do we put this down? So I think what we should do this is a pair at a time. Now, do you want to, maybe what we should do, let's focus over here. Let's do a real quick little cameraman. So let's just so that we have it. This is something that you should be able to do in the margin of your next exam paper if you need to. You should be able to know what the excitation table is for all the flip-flops. Remember how the excitation table works? It works like this. Q at time t, Q at time t plus 1, and then the question is, what is S at time t and R at time t in order to produce that transition? And the possible transitions are 0, 0, 0, 1, 1, 0, 1, 1. Now, do you remember what what does S mean? Set, and R means? Reset. And if it's 0, 0, what does the state do? Changes, no change. Are you with me? So if the transition is from 0 to 0, then what is what's here? 0x, and you can figure this out, right? 0, 0 will keep it unchanged. 0, 1 will reset. Both cases, you'll have a transition from here to here. Are you with me? And now what about this?
1, 0.
1, 0. It has to set it. It can't leave it unchanged. And what about this?
0, 1.
0, 1. So it has to reset it. It can't stay the same. And what is this?
X, 0.
X, 0. So now if you just write this down, all you have to do is look here and put it there. Are you with me? Or if you don't want to put that down, you can just do that all in your head. Okay, but now which columns do we look at to put here? Which columns do we look at to put on flip-flop A? And I think we should do these a pair at a time, right? Because this pair comes right from the excitation table. Okay, so what do we look at? We look at, this is A at time t. We need to look at how flip-flop A is changing. Are you with me?
Right.
So we need to look at this column, the first column, and A at time t, and A at time t plus 1.
Right, so
And because they are 0, 0, so now who was next? I forget, somebody.
Sam.
Yeah, I think you are next, Sam. Okay, so, excuse me. So the 0, 0 means what? 0x. Now, does everybody see how we're doing this? Okay, so next.
0x.
0x. Now, and also I'm not thinking about this, so somebody else challenge if you need to.
X0.
X0. That's all right, take your time. Bum, 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 bum. Alex, I'll take excitation table for 300. Yeah, no, okay, no, okay. Yeah, this don't feel bad. This, okay. Let's think about what it is. Let's think about what it is that we're doing. We're trying to see what the input for the A flip-flop needs to be in order to make the transition that we want the A flip-flop to make. So what do we look at? We look at A at T and A at T plus 1, because that's the transition. And then, so now are you with me? Okay.
So,
X0.
1, 0.
1, 0.
1, 0.
1, 0. Back of the room. Last row. X0?
No. Oh, yeah.
What? Oh, challenge the challenge.
No, no.
Oh, X0.
Oh, X0. There is no XX. X0. Okay.
0, 1.
0, 1. 1, 0. 1, 0. 0, 1.
X0.
X0. Ooh, interesting. Okay. This is all going to be on the next slide, by the way. So,
1, 0.
all right. 1, 0. Now, is everybody's checking? Oh, wait. Are we back?
Yeah.
Yeah.
Oh, okay. Okay. That was fast. We went around fast. Is that 0, 1 or 0, 1? 0. Are you asking me or telling me? I was just teasing.
0, 1.
0, 1.
1, 0.
1, 0. Okay, back of the row again, or back of the room, back row. Zero X. X0. X0. 1, 0.
We're on 0.
Well, we have a challenge here.
0, 0. It's 0.
0X?
Yeah.
Okay. 0X. Okay. 0X.
X0.
X0. 0, 1. 0X. All right, you guys. Good job. I think. Let's check it out. Let's check it out at figure 11.33. So can somebody real quick scan down? We did the whole thing already? You can scan down that quickly? Yeah. Okay, are we good? Okay, so now after we did all this work, it's all up there. We'll erase it all. Because it's on figure 11.33, right? But that was a good exercise. Okay, now what we have to do is what?
Design it. Oh, Carnot maps.
Carnot maps. Now we have to do the Carnot maps. Now tell me, so here's our figure 11.33. How many Carnot maps will we need?
4.
4.
Close, but no cigar.
2.
No, 4.
6.
You were close. 2 is farther away.
6.
5. Good. Because why? We need also a Carnot map for the what? For the Y, for the output. Okay, so now, so we need a Carnot map for SA, a Carnot map for RA, a Carnot map for SB, a Carnot map for RB, and a Carnot map for Y. So let's do, let me see the order. I want to have them. SA, RA. Okay, so let's do SA, again, no peeking. Okay, so here's all our Carnot maps. And this will be SA, and this will be RA, oh no, sorry. We'll do it across. This will be SA, this will be RA, this will be SB, and this will be RB, and this will be Y. And so these are 0, 0, 0, 1, 1, 1, 1, 0. And on top will be our x1, x2. So this will be x1, x2, and this will be A and B. 0, 0, 0, 1, 1, 1, 1, 0. A is the Q output of flip-flop A, and B is the Q output of flip-flop B. And those outputs are going back into the combinational circuit. Are you with me on that? Okay. So, does everybody see how this is working? So this is AB 0, 0, 0, 1, 1, 1, 1, 0. And this is X1, X2, 0, 0, 0, 1, 1, 1, 1, 0. And this is same. All right. Now what we have to do is we have to fill out these tables. You have to fill out these Carnot map tables from the design table, from the flip-flop input conditions of the design table. All right, so now I tell you what let's do. Let's go down. Now let me see. Yeah, let's go one column at a time. All right?
The first one is all numbers.
Okay, so well, who's next? So let's let, and I think we can just transfer column to column because we looked ahead and we were clever in the way we did that, so we don't have to do any transposing here. So this is the, what is this? This is the 0, 0 column of x1, x2,
X.
and we're doing SA
You got X. All the way down.
all the way down.
That's right.
So X, 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 X. Okay, how about this column all the way down? Next.
0, 0, X.
Okay, so 0, and we don't put the zeros, right?
Yeah,
So 0, by the way, I've noticed that some people are still putting your zeros in your Carnot maps, and it makes it really not good. 0, 0, X, X. Okay. Back of the row, back of the room. Column 1, 1. 1, 1, X, X. 1, 1, X, 0. Okay. Is everybody with me here? Okay, what about this one? It's the column for SA, which is I don't think so. It's the column, okay, sorry. Well, okay, first of all, we have to look at SA, right? We're doing SA. So you see with the SA column? All right, and do you see where x1, x2 is 1, 0? Okay, so and then do you see what is the SA for that? So look at the SA column where x1, x2 is 1, 0. Okay, so you're saying 1, 1, 0, x. Is that what? Okay, so now let's do the RA. Oh yeah, and this is because these are all don't care. This input is always don't care. Okay. Okay, so next. Shane. Zero, zero. Okay. Sam.
0, 0, 0,
0, 0, 0, 1,
0, 0, 1, 0.
like that. All right. Input of 0, 0 for x1, x2.
Yeah, 1, 0, 0.
I think you have a challenge. You want to challenge that? What do you think? Next.
Oh.
Yeah, those don't occur. That's the don't care condition all the way down. Okay, so next, 0, 1 column.
0, 1 column.
Oh, I thought 0, 1 column.
Okay, it is 1, 0, 0, 1.
Like that.
Yes.
Next.
0, x, x, 0.
0. Last row. Like that. Okay. Next. Now we're doing RB for input of 0, 0. It's not on there, is it? X1, X2. Yeah, so what is it if it's not on there? Yeah, it's all don't cares. Is everybody good? Okay, so next. 0, 1, 1, 0. Okay. X, 0, 0, X. Next. X, 0, 1, X. And now, oh, 0, 1, X. Sorry. You said it right. Okay, and next. Now we're looking at Y.
X, X, X.
Yeah, because 0, 0 input doesn't occur. Next.
All zeros.
Oh, okay.
0, 0, 1, 1.
1, 1.
1, 1, 0, 0.
Are we good? Okay, now we get out our minimization skills, thinking. What do you think for this one? How can we, let's do SA. How would we minimize this? Top right corner, right? Or top right quadrant. Good deal. How about this one? Ooh, this one's kind of nasty, right? This one doesn't have a neighbor here, a neighbor here, a neighbor here.
Nothing's all, it has to go to the right.
Oh, Pac-Man effect. Okay, and what about this one? None, 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 not even a Pac-Man. Not even a Pac-Man buddy. All right, how about here?
You can get
The square.
Yeah, see, some people were going to do the Pac-Man here, right? And that would have been
Foolish.
not minimum, because why?
You can get the one from this side.
You can include with these. Is everybody good? Are we good? Okay, and this one? These two
With the ones to the two.
with these don't cares, right? All right. And this one doesn't have a buddy up here or over here.
You can do a 4 Pac-Man.
But he does have one here, but yeah, he also has one here and here, right? Yeah, you can do a 4-way Pac-Man. Did you guys see that? Okay. Because we need to cover this one. Are you with me? This is the most the minimized way to cover this one.
Because if you group all four, then it gives you like a smaller variable?
Yes, yes, yes. The bigger the grouping, the fewer the number of inputs you need for the AND gate. Are you with me on that? And now, and how about this one? Ah, another 4 Pac-Man up here, huh? Gesundheit. And now these ones don't have anything here, 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 or here, so we can do these how? Like this. Okay, so now who was next? Let's go around the room and write down the expression. So what is SA?
A prime x1.
Say it again.
A prime x1.
A prime x1. What is this? What are these?
That's
Just A would be the just A would be the bottom 2 rows. Yeah, A, B, so A, B, and then x2 prime or bar, okay. I've been using primes and bars, I guess I should be consistent. Or, now what's this one?
A, B prime, x1, x2.
A, B bar, x1, x2, okay. What about this? What's SB?
X prime, A prime, B prime, or A, B prime, A prime, B prime, X1 for the first one.
Okay, A, there's only one. There's only one.
Is that how that's one?
Okay.
Okay, just the B prime.
Okay, so B,
Just the B prime. Then it's going to be X1 prime without the L.
okay. Are people checking this?
Yes.
Okay, what about this one?
A, x2 bar, or
A, x2 bar, or
B, x1 prime.
B, x1 bar. We skipped, so do you want to do Y? How about, what's this one?
X2 prime, A prime.
And then or.
A, x1, x2.
Is anyone else, is everybody checking this all right? Okay, here comes figure 11.34. Did we do it right? Did we do it? Okay, 1134, figure 1134. Man, we're good. Okay, now what do you suppose the next thing you could do? Get out your templates, but you know, and I think if you drew an abbreviated diagram, okay, so what would it, I'm not going to take the time to erase this and do that and draw it all because we did the hard part. So what would this be? A single SA would be an AND gate, a 1-2 input AND. Let's just count the gates. So this would be what? 1-2 input AND. What would this be?
2 input OR, a 2 input AND, and a 3 input AND.
Yeah, a 3 input AND, a 4 input
Oh,
AND.
that's what I meant, 3 and a 4.
Yeah, so a 3 input AND and a 4 input AND and a 2 input OR. This would be a
2 input AND.
2 input AND. This would be a
2 input ANDs.
2 input ANDs
And a 2 input OR.
and a 2 input OR. And this would be a 2 input AND, a 3 input AND, and a 2 input OR. So there it is, figure 11.35. And now this is abbreviated, but I assume you guys, look, if we look at figure 1135, I assume you guys understand that because we have a B, for example, because we have a B bar going into this AND gate that feeds into the S input of flip-flop B, this B bar would actually be taken from the Q bar here and around here if we didn't abbreviate the diagram. I mean, that's how you'd have to connect it up in the lab. You'd really have to have a wire going there. But does everybody see what it would be? How? And does this, can you visually just make sure that this matches those Boolean algebraic expressions? Because there's a one-to-one correspondence between a what? Boolean algebraic expression and a logic diagram. All right. Excellent. And so you have a design problem for Thursday. And on Thursday then, we will begin. Okay, so now that actually finishes this one little like unit of sequential circuit analysis and design. And so as we did before with the combinational circuits, you remember how we looked at combinational circuit, how we looked at combinational analysis and combinational design with the Carnot maps? And then we looked at a bunch of practical ways to put them together to make a computer. Now we've done the basics of sequential analysis and sequential design. And so starting Thursday, what we're going to do is we're going to see how to put these together in practical devices to make a what? Eventually, on our to build a what?
CPU?
A CPU, a central processing unit, which has inside of it registers.
Program counters.
Program count, yeah. That's our plan. Pretty good, huh?
ALU.
ALU, right. We already know how to make the ALU. But that's going to be in there. All right, good deal. See you on Thursday.